we developed a cell structure on the Grassmannians yesterday, or last time. And so the main thing we're going to talk about today is theorem, the cellular chain complex associated to the Schubert cell decomposition of Grassmannians has no differential, and thus the homology so thus HI of GR in RM is equal to the number of partitions of I into, at most, we can do it either way, but say in numbers which are all less than or equal to, all less than or equal to M minus N. So these are standard kinds of combinatorial gadgets, and that's describing the homology. By the way, a confession, when I was a grad student, there was on TV, there were these, like, I'm assuming they're still there, these weird things that they would advertise, and one was called Grass Man, and he was something that you like put these seeds on and grew hair, and I, on my door of my office, I put this sort of joke that, and I said, what, you know, great mathematician, what happens when a great mathematician has a very bad publicist, right? But anyways, so this is the theorem that actually you've got this cellular chain complex, and this is mod 2, and that's key. This is definitely not true over the integers. When we start doing complex things, we'll see that an analog of this statement is true over the integers. Let me indicate various lines of proofs that we'll discuss. You can do sort of direct, degree calculations. Of the CW differential. We'll talk about that. Another thing you can do is that use these Schubert, blown up Schubert varieties, but actually, I mean, if use the closures of cells to produce homology. Again, to make sure you would, so you can take for example, we had something Schubert variety that was a closure of a cell that was a quotient of a Klein bottle, and you just take the Klein bottle and map it to get a homology class, and then also use them to produce cohomology as through tome cochains. And then what you can do is get a lower bound on homology and cohomology through pairing them. So these are both sort of roll up your sleeves and do some real geometric work, as some people would say. But then there's a trick, and that is, this again assumes the Whitney sum formula. And that is to map to cohomology of a product of n copies of RP, whatever, capital N's. So that's gonna those are three different strategies. So I prepared the names of the cells for the Grassmannian of two planes in R4. The degrees go down from 0, 1, 2, 3, and 4. You can read off the degrees from the number of shaded blocks. So here's our list of Schubert cells. So I wanted to illustrate some of these roll your sleeves up techniques. So let's talk about the computing the differential in the cellular chain complex. So the point is that that differential is given, excuse me, by some degree. And what you can do is you fix a point in an n-1 cell. So suppose I want to understand a coefficient of the differential. The differential's linear map. I can think of that as a matrix. I'm just trying to compute one number in that matrix, and that number is given by take a point in somewhere in the interior of an n-1 cell, look at its pre-image, and and maybe, so if the attaching map of this maybe wraps around a few times, then especially if I count with pluses and minuses, then this attaching map will have degree 4. And so the way I often think about that in, so this is my picture of DCW. Oops. And the way I like to think about that is that, this is happening within some larger space. So this is my disk mapping in there. So the interior of this disk is mapping in here. And again, maybe I think about that disk folding, but the point is that I like to think about different ways that I can be in the interior of this disk and approach the pre-images of that point. And again, maybe this is kind of folded over, right, sandwiched or wrapped or things like that. So all these different ways to approach this would give me all sort of different ways in the space that I'm in the interior of the cell. But I like to think about it in both places. I like to think sort of both up in that disk, but also in the space itself as I'm doing this calculation. So how does that work here? Let's give an example. Let's go from degree 2 to degree 1. So let's remind ourselves that this first this first degree 1 cell are subspaces W, which are planes. They contain the first element of our flag. I'll call that V sub 1, but you could also think R1. And they sit in the third element of the flag. And then I have to, I'm just sort of thinking about, well, they contain V1, and then they contain some other line through the origin, and thinking about that line in V3 mod V1 gives me a copy of RP1. So this is a 1 cell. And what are these two cells? One corresponds to, well, it's pretty similar. If I go to the left, let's see. That first picture is, well, this is where I like to have all the combinatorics in front of me. This first step up says I contain V1 here. This means I contain, the first element of the flag. And then there's, every time I step to the right, there's no further conditions. And every time I step up, there's some kind of condition. So this is really, V1 is contained in W is contained in V4, and that's an RP2. And then this other Schubert cell says that, well, the first step means I don't contain V1, but my second step up, this little edge here, means that I intersect V2 in a line. So I've got V2 intersect W is some line, and also W does sit inside of, then by the third step, I have all of W. So W does sit inside V3. All right. And so we think about these. Again, this is an RP1. This is some sort of Klein-Bodily thing. But that's in the closure. Now let's think upstairs, just the closed cell, which we had put inside the space of frames. You might imagine that the attaching map from the disk onto RP1 to make RP2, we know what that needs to be, but let's just look at it more geometrically. What this says is I've got, let's take a W in the interior. So that's just some W that contains V1 and then is contained in V3. So it's some plane in, schematically it's a plane, but it contains V1. So this is inside there, but then it's in R3. And the nearby planes in the Schubert cell on the left, upstairs, if we think about the way we parameterize these by half spaces, that plane that sits in R3, I can deform it to, or I can approach it using the picture above. How can I approach something that sits in R3 from a series that's coming from a sequence in R4? Well, I can either tilt down this way or have tilted up that way. And so what we see is that, and again, what you have to do is complete the cell to a disk, and just notice that because I used this particular basis vector approach to parameterize the cell, there's, let me draw this a dimension down, because that's the limits of my artistic abilities. At the very bottom, this actually occurs at the very bottom, you have this line, which is V1, and you ask, okay, now if I'm thinking about the lines in V2, and this is being parameterized by this cell here, and I'm choosing my basis vector. Well, there's exactly sort of two deformations of this line down here that are sort of nearby, two different sequences of those. One uses these basis vectors to the left as the line tilts down. The other uses the purple, if I think about the purple, that's another sequence of lines that have limit to the same line there, and they're very far apart in the closed disk. So I've got a closed interval, different sequences of points which approach the line in question. Again, you don't have to think in terms of sequences. I find this sort of helpful to make these calculations because I'm thinking of that interior of the disk as a way to track the different boundary points that hit a particular point. So this attaching map, this first attaching map here is the same picture, sort of a dimension up. I've got my W, or maybe even two up. W is a plane inside R3 or V3, and I'm just thinking of different planes in R4 that and just there's a one-dimensional family, so that's why it's codimension 1, because everybody contains V1 that approach it. What about this other differential here? So then I've got V2 intersect W is L, W is inside V3. So now W sits in V3 either way. And then the question is, okay, how do we degenerate from V2 intersect W equals L to V1 is contained in W? Well, of course, L can approach V1. And now we have exactly the picture that I wrote down below of those two different L's that can be the intersection of W with V2. And again, in the way we saw cells, we would see these basis vectors that we're using to parameterize the cells be on opposite ends of that attaching there. So this one's interesting because it's, I mean, what is the dimension of the cell? Well, it's a 2 cell. Its boundary is a 1 cell, but we're actually just seeing the that disk is naturally coming as interval cross interval, and we're really just seeing the attachment on the two ends there. We aren't seeing anything on the other two sides of the square. But in any case, the point is that throughout every one of these cases, one can define an involution. Let me go ahead and write some things up here. You define an involution. So find an involution on attaching spheres, on the attaching spheres, which carry the preimages of a fixed point, preimages of the chosen points in the cell of a dimension less to each other. And so then mod 2, things come in pairs. Of course, there's lots of transversality here, but that's how that would go. Okay, next. Next, I said, let's think about both homology and cohomology through tome cochains. So, so what should I do? Should I erase or maybe work? Maybe I can work to the right. So what's a very simple example of this? So we know there is a class. So the RP1, which is the Schubert variety associated to this Schubert cell, that's mapping to GR2, R4. So that implies a class in H lower 1. But of course, it's a cycle. I want to know, is it a boundary or not? And because CW structure says that actually there's at most one homology class, but maybe this occurs on the boundary of something. But I've got this class here, which is, we're thinking of it as a 3-cell. And what is this? This was some sort of RP1 kind of twisted product, RP2 modulo something. That maps to, but let's not do the modulo. That's mapping to GER to R4. It would give a class in H3, don't get me wrong, because I can take its fundamental class. Or I can think of this as a tome cochain, and I also get a, because it has no boundary, tome cocycle, and we get a class in H upper 3. And what I'm going to do is going to argue, and we, again, maybe that's 0, maybe that's the boundary of something. But if it pairs non-trivially on some homology class, then I can deduce both that class and the homology class are non-zero. More generally, if I have a collection of things, I compute the pairing matrix. If it's full rank, then I know that both sets of homology and cohomology are independent. So that's what you need in the middle dimension. But I'm just going to do this one example. What we're going to do now, let's maybe set the standard. Well, this is a class in H1, and again, what did we think of this? It was, so this was V1 contained in this W contained in V3. Let's use a different flag here. The flag that I want to use here, let's call it, call the flag U1 inside of U2, etc. And then, and the reason I'm going to do that, and let's just assume these intersect the VI generically. In other words, the codimensions always add, so generically, transversely. And then in this flag, this twisted RP1 and RP2 was really the blow up of the class that's defined by W intersect U2 is some line L. Okay. And what I want to do is argue that the pullback, really the intersection, because let me sort of think of the images here, is well, just an odd number of points. So this is a codimension 3 object, well, codimension 1 object, sorry, dimension 3, codimension 1, and I want to intersect it with that RP1. Well, I just look at these two conditions and I say, how many times does that happen? Well, W is contained in V3, that's a restriction. V3 intersect U2 is a line. That's got to be the one that I can use to complete W1. So that implies that the intersection of these two, so the intersection is the unique W, which is the span of V1, because the W must contain V1, but because W intersect U2 is L, I've got to take the span of those two lines, and that's a two-dimensional subspace. There's lots of transversality to check, but that's pretty straightforward. So that would be technique number 2. You would actually produce homology and cohomology enough to show that the cellular structure, the CW complex, predicts at most this number of partitions homology, but we realize that we say we've got at least that much homology and at least that much cohomology because I'm I'm showing you directly that these are independent classes. So I have at least that rank by this intersection pairing argument, and at most that rank because of the CW, the cellular chain complex. By the way, chain complexes, spectral sequence more generally, they're upper bounds. So we can at least culturally draw on our experience taking analysis classes and knowing that, okay, you can think about upper bounds and lower bounds and then trying to bring them together. And that's a useful framework to think about this particular technique. On the one hand, I've got a chain complex or a spectral sequence that's giving me an upper bound. On the other, if I can just produce a lot of homology, cohomology, that gives me a lower bound. And so we get the results stated. Moreover, I mean, we get more. This not only tells me what the ranks of those homology groups are, but it's what I would call a complete presentation. I would have a basis and co-basis in each degree. So a spanning set and a way, you give me anything else, I can intersect it with these Schubert varieties and tell you what linear combination it is of my homology basis, or vice versa if you'd like. So this technique is more labor intensive. Don't get me wrong, I'm gonna really love the third technique, and it's also more labor intensive than the first technique. But especially compared with the first technique, we're getting not just a calculation of homology groups, but we're also really seeing the a complete presentation for homology, a basis and a co-basis. So a basis for homology and a basis for cohomology. Okay, so let's remind ourselves, we're almost there. Technique number 3 is, I'm going to, and let's go ahead and we were talking about finite Grassmannians. You can take the union of these cell structures, they sit into each other naturally. I think I won't dwell on that, but that's pretty straightforward. It actually works well. I'll leave that as an exercise, like think about inclusions of one Grassmannian into the next in terms of the pictures of these cells. How does the cell structure go when I pass from Grassmannians in 10, 3 planes in 10 dimensions to 3 planes in 11 dimensions. Also, I could even do like 4 planes in 11 dimensions by taking direct sum of the trivial bundle. There's all these maps that are, many maps that we want to understand can be understood in this, are cellular. But then, so then the final argument we already made, essentially. So what we, recall that we showed that Wi of a direct sum of however many I want. So j equals 1 to some n, and I guess it has to be at least I, of the tautological line bundle. This is now sitting over RPN, RP infinity. I won't say which RPN, so I'm just going to call it gamma 1. This is the isometric polynomial inside the cohomology of the product of these RPNs. I should not conflict there, so I don't know, call it RP capital M or something like that. But that's manifold, so maybe RP capital D for high dimension. Or even let's just say RP infinity. Okay, great. So we've got these elementary symmetric polynomials, but what that says is that, but the classification theorem, and we prove this, what I just stated was a straightforward application of the Whitney sum formula. You look at the total Stiefel-Whitney class of gamma 1, it's just 1 plus you'd often call it x sub I, the generator of the ith product factor of an RP infinity. And you multiply out 1 plus x at 1 plus x1 times 1 plus x2 times 1 plus x3, and you see these symmetric polynomials. So by the classification theorem, W1 of this gamma n is going to map to this W1 of a product of these gamma 1s. And what you find is that because, and this is Wi, right? And so you calculate, but let's just say this, F2, you calculate the image in cohomology inside of, again, this is symmetric polynomials, F2 adjoin x1, xn. But you end up with symmetric polynomials. The rank of, so you're let's say this, so cohomology of grn, let's go up to R infinity, surjects onto that. But you then see that, so this number of partitions is a lower bound. You can't surject onto something with lower ranks, and this polynomial algebra in sigma 1, sigma 2 has rank 1 in degree 1, you just have sigma 1. Rank 2 in degree 2, you've got sigma 1 squared and sigma 2. 3 in degree 3. 5 in degree 4, because you've got sigma 1 to the 4th. Sigma 1 squared, sigma 2. Sigma 1, sigma 3. Sigma 2 squared, and sigma 4. And all of these, you see partitions, and it's actually essentially the same block picture because, again, this now tells you we have a lower bound. The existence of a cell structure tells you we have an upper bound. When they agree, of course, then the cell structure, the cellular chain complex had to have no differential. So that is the third proof. That's the only one of the three that's complete. 2, roll up your sleeves proofs, calculate DCW by finding an involution. The second thing would be find, intersect Schubert varieties. You have to pick alternate flags. And then the third thing, Schubert varieties between different flags. You'll have a hard time getting good results if you just use the same flag for both. And here is just mapped to the cohomology of RPN, and you see that an isomorphism with this symmetric polynomials. That is by far the slickest proof, the one Milner and Stasheff give, but I wanted to give a different one. All right. Exercises, there's a corresponding section of Milner and Stasheff. I think it's chapter 7. We can, looking at those could be useful. Making some of these intersection calculations, looking closely at some DCW, just any of these could be fleshed out. All right.